Hello there, I am Diana and I will be talking about nanoclays in food and beverages packaging. As we know, packaging is that exterior shell that covers our food and beverages to maintain them ready and safe to be consumed. Even though its existence on the market is quite old, it keeps evolving in order to achieve consumers' new demands. Food package has two main roles: a passive role that leads smart protection, detection, and communication, and an active role to extend food shelf life, the reduction of contamination by releasing or absorbing substances into or from the packaged food or the environment surrounding the food, which will mainly lead to the consumer's health and safety. Other objectives of food packaging are recording, tracing, and providing important information about the changes in quality or conditions of the packaged product. So, why will nanoclay be considered to enter the polymer matrix for food packaging? Nanomaterials do not have a good reputation when it comes to toxicology. Nanoclays are nanoparticles made of layered mineral silicates mainly composed by oxygen and silicon or aluminum. Nanoclay is the most promising nanomaterial within the food packaging technology field. In 2014, the nanoclay market reported $343 million and is expected to grow by 2022. Nanoclay is capable of improving barrier and mechanical properties as well as water solubility by adding less than 10 weight% into a host polymer matrix. Clays are not expensive, so there is a cost-effective advantage. Anyhow, what needs to be considered to apply nanoclay in a package is the type of polymer and nanoclay, loading content, processing technique, desired properties and applications, and after effects such as color alteration, change in elongation, or surface roughness. Nanoclays possess platelet form, flaky soft structure, low specific gravity, and high aspect ratio with nanoscale thickness. Specifically, montmorillonite MMT and organophilic MMT are the most common nanoclays for researchers and industries due to their high surface area with a reasonable aspect ratio of 50 to 1000 and good compatibility with most of the organic thermoplastics. However, MMT is only miscible in hydrophilic polymers, and most of the food packaging is hydrophobic. In order to induce the MMT polymer compatibility, an organophilic host matrix is used and the hydrophilic silicate surface is modified through ion exchange reactions with ammonium salts, resulting in a lower surface energy and higher affinity with polymer. A polymer nanoclay composite can be prepared through different techniques, but the most common is melt intercalation because it is cost-effective, simple, feasible, and an environmentally benign process. In this preparation method, a nanoclay is blended with a polymer by shear force at a temperature above the softening point of the polymer. The shear force from the blending process alters the orientation and dispersion of the nanoclay in the host polymer. In Figure 2, the three different orientations are presented. In normal dispersion, the nanoclay is within the polymer. Meanwhile, in intercalated dispersion, the polymer is located between the interlayers of the stacked nanoclay platelets. And for exfoliated nanocomposite, the individual nanoclay platelets are well separated and randomly dispersed throughout the host matrix. Also in this figure, there is a cross-section of a low-density polyethylene nanocomposite film with 10 weight% of nanoclay, in which its parallel orientation was initiated by the shear force during the extrusion and film forming processes. Nanocomposites produced at an industrial scale are provided by enterprises such as Nanocore, Aegis, Urethane, Nanotube, Imperm, Colormetrics Corp, and Nanoseal. Nanocomposites manufactured by melt intercalation results either in the form of a rigid bottle container for beverages or a flexible film for fresh and dried food. Some commercial examples of DB are DB Mayer bed bags for bread storage, a Saica Everfresh bag for fruits and vegetables, Plantic in plastic tray for Cadbury's product dairy milk, and Marks and Spencer Swiss chocolate. Beer bottles from Miller Brewing and Heat Brewery Corporation, and packaging for ready-to-eat meals for soldiers and astronauts from the U.S. military and NASA. Nanoclays offers extra characteristics applicable for active and intelligent packaging, antimicrobial agents, colorimetric indicator, template, and biodegradability stimulator, among others. Antimicrobial agents, for example, OMNT, show strong antimicrobial functions against gram-negative and gram-positive bacteria, probably due to the quaternary ammonium groups from surface modifiers. In the case of colorimetric indicator template, a study reported impregnation of blueberry extract in between the interlayer of nanoclay platelets. The anthocyanins containing MMT and OMMT powder showed good response to the change in pH for both acidic and alkaline mediums. The larger basal spacing of OMMT allowed more blueberry extract, and therefore the color change was more intense. It could be used for fresh food of fishery products and meat. In the case of a biodegradable colorimetric indicator film for monitoring milk spoilage, a starch clay nanocomposite film was fabricated with a pH dye and attached into a milk bottle. It reduced water solubility of the starch-based film and restrained a dye release phenomenon into the milk. Discarded packaging is usually handled by composting, degradation, landfill, combustion, and recycling. Thermoplastics might be inert to the natural environment, becoming a real non-degradability issue, and it is preferred that a plastic is able to perform degradation in the biosphere because of the shorter degradation time and less energy consumption. For petroleum-based polymers, abiotic degradation can be started by photoirradiation or thermal energy in the case of OMMT. The main risk of nanoclay is to swallow the contaminated food from food packaging, which is likely to be through potential migration of both nanoparticles and the dissolved form of aluminum and silicon. Studies showed migration of aluminum as particles and dissolved ions from DB Mayer bread bags and a Saica Everfresh bag, which occurs faster at acidic mediums. On the other side, migration rates of nanoclays was demonstrated to be less than that of the sulfur nanoparticles at the same conditions, presumably because of the different morphology among these two materials. Nanoclays comes in a platelet-like presentation. Meanwhile, silver nanoparticles are spherical, embedded on the surface of the polymer. It is important to note that there is no framework or a specific migration limit on nanoclay or silicon food regulations. In 1990, the Council Directive 91-2A EEC set a general migration limit of constituents that could migrate into food of 10 mg per decameter square for the migration of chemicals from plastics to food, meaning that the nanoclay market is within the range since it has a concentration of less than 10 weight%. And as a conclusion, compatibility with polymers has to be induced by modifying its surface with ammonium salts, making it available in the market. Second, several researchers offer additional advanced features for food packaging materials, antimicrobial agent, control and release for active ingredients, colorimetric indicators, and such. And last but not least, the absence of legislation on nanomaterials concerning consumers and environmental safety seems to be a constraint to the use of films of clay nanocomposites in food packaging. However, available migration studies have revealed that the diffuse levels of aluminum and silicon in such containers are within the limits of current regulations. This work was based on Nanoclays in food and beverage packaging by Bumbut Sanforoki and Co. If you would like to know more about this interesting topic, I invite you to read the whole paper.